I'd like to thank the organization for this opportunity to show this work. I'm going to talk about nucleon electromagnetic and axial form factors in light front constituent part model. The presentation plan is composed by 5 parts. Ingredients used in our nucleon model, general considerations about electromagnetic and axial form factors, written in terms of light cone coordinates, obtain of nucleon electron current, numerical results, and conclusion. The main aspects in our model are the effect of scalar spin coupling on nucleon electron properties, introduction of high momentum scale components in the wave function, introduction of a high momentum in our model that shows a reasonable description for static observables, and the ratio between proton electric form factor and proton magnetic form factor compared with experimental data. Better description of nucleon electroweak properties can be obtained by 2-scale wave function, which is constructed to fit of neutron magnetic moment. Here, there are the main reference of nuclear model in which we are working. The first step of this work is the effective Lagrange. We have chosen scalar spin coupling between quark and nucleon fields. In this Lagrange, we identify the Pauli isospin matrix, the totally antisymmetric tensor in color space, the conjugate quark field, where C is the charge conjugation, N index, N is the nucleon mass. The electromagnetic form factor is obtained from the plus electromagnetic current, written in light front coordinates with Del-Young condition. F1 and F2 are the Dirac and Pauli form factor respectively. The nucleon electric and magnetic form factors are obtained from Sachs form factor written here, and the nucleomagnetic moment and nuclear square radius are obtained from square momentum transfer equals 0. In the same way, the axial form factor is obtained from plus component in the light front of axial currents. The axial coupling constant came from the axial form factor in the new plane momentum transfer. We have calculated both electromagnetic currents and axial current in bright frame momentum, where P and PL are the momentum of the nucleon before and after quark off-shell absorbs photon momentum transfer. In the electromagnetic and axial current, we have used light front spin. In our calculation, we have changed Dirac spinor to the light front spinor through the Melo rotation given by this expression. Here are the Feynman diagrams obtained from effective Lagrange. In all diagrams, we have chosen the quark width as the quark that absorbs photon momentum transfer. The quarks 1 and 2 are considered as quark spectator on mass shell. Here it is the plus component of nucleon electromagnetic current operator, and we show only the JA plus. In the same way, we have obtained JB plus, JC plus, and JD plus. Lambda here is chosen to introduce 3 quark momentum space wave function after integration of over energy in the light front K minus. In this loop integral calculation SP is the final propagator, SC is the conjugate final propagator, and Q is the charge operator. After integrations over light front energies, we insert momentum part of the wave function through this exchange. In this expression, the final wave function after the quark absorbs the photon and the wave function before quark absorbs the photon. Here, K1 and K2 are considered quarks on mass shell. In all J plus microscopic current, the argument of the wave function is the squared mass of three quarks. The argument of final wave function is the squared free mass, which the quark free absorbed photon momentum transfer. I show you here the plus component of axial current and the construction of microscopic components has the same steps as I have said before. Again, the integrations over K minus by analytic integration, we have obtained integral in terms of light front kinematic momentum to be made by numerical calculations. I also observed that the plus component of axial current D is equal 0. The two-scale wave function that we have used was power law wave function, in which the first part belongs to low momentum scale, while the high momentum scale is connected with 0 of proton-electron factor. pH is related to possible definition of the high momentum scale brought by two-scale wave function to be the value of free mass at which two terms are equal. In numerical results, we have studied three kinds of wave function. Set one parameters chosen to reproduce better the magnetic proton momentum. Parameters choose to reproduce better the neutron magnetic momentum. One scale beta parameter choose to fit the experimental neutron magnetic moment. Here, I show you tables of wave function parameter and the static observables. And we can see in the set 2 the nice value of neutron magnetic moment and the 0 of proton electron factor moved to 15 GeV squared. One of the correlations that we have studied and present here show that the two wave functions set 1 and set 2 preserve a good feature already achieved in describing the nuclear static observables by one wave function scale. Now, I'm going to show some discussion about axial coupling constant. Before that, it's important to observe the difference between final construction and Baca-Thomas construction. The first one is the construction used in our model that coefficients of Melo's rotation of quark spin have the arguments defined by the momentum of quarks in pair, and the nuclear rest frame constrained by total momentum. On the other hand, Baca-Thomas construction, the arguments of the Melo's rotation are defined in the rest frame of free constituent quarks. Here we compare expressions of GA according Baca-Thomas construction and GA from our model. I show you three aspects of this analysis. The limit of a point-like nucleon GA tends to 5/3 for set 1, set 2, and 1 scale. For 2-scale wave function, GE values become larger than 1.06 for set 2 and 0.68 for set 1, with beta similar 0.4 for both sets. The limit beta to 0, GA from our model become larger than these respective values. In the next figures, I show you 3 results for 1-scale wave function and 2 results for 2-scale wave function. We can see in the normalized axial vector that set 2 shows a nice agreement with experimental data. I remember that the parameters chose to reproduce better neutron magnetic moment. On the other hand, set 1 and 1 scale that fit proton magnetic moment show bad agreement with experimental data. This figure is one of the most important for our work. There is here a comparison between set 1, set 2, and 1 scale. We can see that the zero of proton electron factor is moved by introduction of a high momentum scale. By seeing a neutron electron factor, we can note that set 2 also show a nice agreement with experimental data in low square momentum transfer, in opposition for set 1, which shows bad agreement. Finally, I'm going to show some conclusions of our work. By introducing high momentum scale in 2-scale wave function, we can describe better the ratio between proton electric and proton magnetic form factors without destroying the good description of the nucleostatic properties obtained by 1 wave function, 1-scale wave function. The best description is achieved by 2-scale wave function with parameters of set 2 that are chosen to reproduce neutron magnetic moment. In our study for axial constant coupling, the best achievement was also obtained by set 2. A similar behavior can be seen by using 2-scale wave functions in our model for proton and neutron magnetic forming factors. I would like to thanks again to organizing for this opportunity to show our work. Thanks for your attention.